Hello, everyone. I I'll be discussing a topic in reading analysis in this video. I have topic on series. The first one will be summation by parts, products, rearrangements, and absolute convergence. In this video, I'm going to be taking it piece by piece. So um, the first part is the summation by part. So I'm going to be looking at this theorem. So if we have two sequences, AN and BN, and we define the partial sum in this form for AN, so capital AN equals the sum from K equal to 0 to N of AK for N bigger or equal to 0, and A minus 1 is taken as 0. So again, we are given two sequences, AN and BN, and we define the partial sum of AN in this way. If P is less than Q, positive numbers, then we'll have that the series given by A and BN this way is equal to the sum from N equals to P to Q minus 1 of AN into BN minus BN plus 1 plus AQBQ minus AP minus 1BP. The last two terms here are not part of the sum. All right, so let's just look into the sketch of the proof. By definition, we are given that the partial sum, capital AN, is given at this, so I can write it out explicitly to be A0 plus A1 plus all the way to AN minus 1 plus AN. And of course, I can also write AN minus 1 in this way. So that would be A0 plus A1 plus all the way to AN minus 1. Now, obviously, when I subtract AN minus 1 from AN, you will realize that the terms will cancel out. So A not cancel out, A not, A1 cancel out, A not onto the term of AN minus 1. So which means that AN minus 1 is just the small an. If that is the case, I can go back to the sum. So the sum from n equals to p to q of an, bn, all I am doing here is to replace little an by capital AN minus an minus 1. So I'm just replacing what we derive here in this place. All right, so the next step is that I'm splitting the sum. So I open up the parentheses and I splitted the sum into two. Now I'm going to be looking at each of them separately. So in the second sum, I'm going to be changing the variable. So when I mean the second sum, I mean this part with capital AN minus 1 BN. So if I let M2 be N minus 1, and I can get N equals to M plus 1, also, n equals to p implies m equals to p minus 1, and so on. If you replace this variable into the second sum, which is given like this, so you're going to be getting this sum. So all I'm doing here is to replace n minus 1 by m. N here is replaced by m plus 1, and then p is replaced by n equals to p is replaced by m equals to p minus 1. Since these the variables, these m, n, and all that, they are just dummy, so I can rename it back into n. That's allowed. And of course, so I have transformed the second sum from the previous estimate we have in the previous slide into this by changing the variable. Of course, in order to make any combination for the sum, you need the index to start from the same place and end in the same place. So we still need a little bit of work to be done here. All right, so write each sum by separating off the end terms. So what I do in the first sum, in the right-hand side of this equation, I try to have the end point to be q minus 1 so that it's matching with this second sum. And you only do that by just separating the q term. So I just pull out the q term. When n is q, you have aq plus aq bq. And so the sum stop at q minus 1. Also for the second term here, this is ending as q minus 1, but it's not starting at p. So I pull out the p minus 1 from here so when n is p minus 1, I have ap minus 1 times bp, because now you have n plus 1. So if you put in n equals to p minus 1, the minus 1 will cancel out. So that's this term here, and then we have this sum now look exactly like this sum in terms of where it starts and where it ends. So when you combine the two of them, we are able now to combine the two sums with these extra terms. So now we go back to the original series. So we have this series coming here. Then this is the first piece we did, and this is the second piece. And obviously, we can combine this sum here, the series here with the series here, and then keep these terms separately. And once you do that, that's exactly what we are looking for. And so that is the proof of the summation by parts. I just want to be careful. The summation of A and Bn is not the same thing as the product of sum of series An and the series given by Bn. This is completely a different expression. All right, so let's see how this is now being used for something called the Dirichlet test. So if I'm given a series An, and then the partial sum is defined with this way. So the assumption is the partial sum is bounded, which means there exists some positive number such that the absolute value of this is less than n for all n. Also, we assume that the second series Bn is decreasing. And the sequence Bn is decreasing, and then that sequence converges to 0 as n goes to infinity. Then the summation by parts series converges. So the series given by this n equals to 0 to infinity an bn converges. So let's also briefly see the proof of this. So by the hypothesis, we know that an is bounded, so we are guaranteed that there is n such that this is true. Also, if we let epsilon positive be given, since Bn converges, we know that it is bounded, so there exists some capital N for such that this is true. The choice of this band actually is helpful as we continue the proof. All right, so I'm going to be selecting this band. Q is bigger than P, while P is bigger or equal to N. So the tail end of the series of the series that we had is given this to be this. So n equals to P, sum from n equals to P to Q of A and B n. Now we know what this guy looks like from the previous theorem that we just proved. We have shown that this series equals to this. And if that is the case, then if I take the absolute value of both sides, If I take absolute value of both sides and use triangle inequality, I'm going to have less or equal to absolute value of the first term plus absolute value of the second term plus absolute value of the third term. So I'll take absolute value of each piece. So that's exactly what I'm doing here. And then again, because the absolute value of the sum, I can use triangle inequality in the first term in the right-hand side also, right? So it's going to be less or equal to the absolute value of this. Now, an is bounded by m, so we pull out the m now that is not dependent on n any longer. So we have this, all the absolute value of this is less than m with this series this. Observe that this series is telescoping, meaning that if I write it out explicitly, b1 minus b2, in this case, n is starting from p, so I'm going to have bp minus bp plus 1 plus bp plus 1 minus bp plus 2. So the terms in between will cancel out. So the only thing that survived there is the starting point bp and the ending point bq. So all these series terms, if you write it out explicitly, the middle terms will cancel out. That's called telescoping series. So I'm going to be, all this sum here is just bp minus bq. Also, that's the first time that we just estimate the band. The second term in the right-hand side here, we can also bound it because AQ is bounded by M. So we have this AP minus 1 is also bounded by M. We have this. All right, so if I plug in everything back into the original sum, I know the band for this, I know the band for this, and I know the band for the third term. Eventually, this is what I get. And if I write it out explicitly, M is common, I pull out N, you can see that BP added to this BP, you have 2, but minus BQ plus BQ cancel out. So what we get eventually is 2MBP. Now, remember the band. We are aware that Bn is decreasing. So if I have P bigger or equal to N, it means that BP will be less or equal to Bn for a decreasing sequence. So what that means is that if I go back to the previous estimate here, so the absolute value of the estimate I'm looking for is less than 2MBP, but BP is less than Bn. And also initially we know that sequence Bn converges, so it is bounded, so we can bound it. There is some n for which this is true. Now you see where the estimate comes from, because eventually we needed to get an epsilon. So if I multiply this together, 2n cancel 2m, and I'm going to be adding epsilon. All right, so for every epsilon, there is this n such that for all this q bigger than or equal to p bigger than or equal to n, the absolute value of this series is less than or equal to epsilon. Of course, we have done that. We have done this, that if this is true, it satisfies Cauchy criterion, and that means the series in the absolute side, the absolute value converges. And that is the proof for this theorem. And that is where I'm going to be stopping in this particular video. I am going to be recording the next video, and that will be talking about absolute convergence. So watch out for my next video on this. Thank you very much.